Let us learn electron spin resonance (ESR) and its basic principle. Electron spin resonance or electron paramagnetic resonance (EPR) or electron magnetic resonance (EMR). ESR detects transitions between energy levels of unpaired electrons. It uses microwaves and a magnetic field to induce transitions. One can study materials with unpaired electrons such as radicals, transition metal complexes, and biomolecules. It is applied in physics, chemistry, biology, archaeology, and so on. Electron spin resonance (ESR), also called as electron paramagnetic resonance (EPR), is a spectroscopic technique confined to the study of those species having one or more unpaired electrons. It is a type of spectroscopy that uses microwave radiation and a magnetic field to study paramagnetic species and their interactions. The method takes advantage of angular momentum of the electron and its magnetic momentum to reveal wealth of information. The angular momentum may arise from both spin and orbital motions, S and L. It is associated with the angular momentum. There will be a magnetic moment. Explanation. Electrons possess an intrinsic property called spin, which acts like a tiny magnetic dipole. In most molecules, electrons come in pairs with opposite spins, cancelling out their magnetic effects. However, molecules with one or more unpaired electrons, paramagnetic species what we call, exhibit net magnetic moments. When a sample containing unpaired electrons is placed in a magnetic field, the energy levels of these electrons split into two distinct states, corresponding to the two possible spin orientations, spin up and spin down. If the energy difference between these two spin states matches the energy of the microwave radiation, the unpaired electrons can absorb the microwave energy and transition between the spin states. ESR measures the amount of microwave radiation absorbed by the sample as the magnetic field is varied. This absorption pattern provides information about the electronic structure, chemical environment, and dynamics of the paramagnetic species. The principle of ESR is analogous to nuclear magnetic resonance (NMR), but instead of studying the magnetic properties of atomic nuclei, ESR focuses on the magnetic properties of unpaired electrons. ESR has a wide range of applications, including studying free radicals, transition metal complexes, reaction kinetics, and the structure of the materials. Theory. The spin and charge of the electron confer on it a spin magnetic moment mu s is given by mu s equals minus g mu b s by h, where g is the gyromagnetic ratio and mu b is the Bohr magneton. If angular momentum is expressed in h, equation 4.1 reduces to, so this is Bohr magneton. Mu s equals minus g mu b s, where capital S is replaced with small s by h. Also, the orbital magnetic moment mu L is given by mu L equals minus mu b L, where L is the orbital angular momentum of the electron in units of h. So the total magnetic momentum is given by adding these two. Mu L equals mu s plus mu small s. So this is not mu L, this is mu. So capital mu equals mu s plus mu L, which is equal to, adding these two equations, that will give us minus g mu b s minus g mu b L. In most of the interests, the magnetic moment arises from spin angular momentum only. If the system has only spin magnetic moments, then that equation 4.4 becomes mu equals the contribution only from spin. So we have minus G mu B S. The negative sign indicates that mu and S are in the opposite directions. Among the large number of paramagnetic systems, the most important ones are transition metal ions, free radical ions, and molecules having an odd number of electrons and so on. It is based on the resonant absorption of microwave radiation by molecules possessing unpaired electron or odd number of electrons in the application of magnetic field. It is basically used for paramagnetic species, free radical, biradicals, triplet states, conduction of electron in a metal, transition metal, and metal complexes. Consider a simplest case. When a species having one unpaired electron is kept in a magnetic field, then, and this is ms equal to plus or minus 1 by 2, which is when in the absence of magnetic field, and this will have degenerate values, plus 1 by 2 and minus 1 by 2, which is nothing but degenerate values. The moment when you are going to apply magnetic field, and there will be a split, and this is ms equals minus 1 by 2, which is a lower state, lower energy, and ms equal to plus 1 by 2, which is considered as higher state, higher energy. The differential energy del E, which is nothing but the H nu, which is the radiation which is coming inside, microwave radiation. So H nu, which is equal to G mu B B. Usually that higher energy is considered as alpha spin state and lower energy is considered as beta spin state. So here mu B is the Bohr magneton and B is the strength of magnetic field, where G is the spectroscopy splitting factor or G factor or Landau splitting factor, and for a free electron the value is G equals 2.0023. But in compounds, this value G is altered by spin orbital coupling, which changes local magnetic field experienced by the electron. Usually in ESR spectroscopy, microwave frequency is kept constant and the applied field strength is varied, that is B is varied. The principle of ESR. When an electron spin having magnetic moment mu is placed in the magnetic field B, then the interaction energy is given by E equals minus mu dot B, which is equal to minus mu B cos theta. Here theta is the angle between mu and B. As cos theta equals ms by s, substitute the value of mu from equation 4.5. So equation 4.5 is given as this, and instead of cos theta you can substitute ms by s. Then we have E equals, so substituting for mu from this expression, equation 4.5, then we have G mu B B ms. It may be noted here that we considered only the spin magnetic moment. Since spin S is equal to 1 by 2 for an electron, so instead of ms we can substitute plus or minus 1 by 2. Then we'll have two levels with the energies, E minus 1 by 2, which is given as minus 1 by 2 G mu B B, and E 1 by 2, which is equal to 1 by 2 G mu B B. In the absence of magnetic field, which is D equals 0, the two values of ms will give rise to a doubly degenerate energy state. If a magnetic field is applied, this degeneracy is removed, broken by splitting the energy levels as E minus 1 by 2 and E plus 1 by 2 as shown in the figure, like this. So that will be split into plus 1 by 2 and minus 1 by 2. The low energy state will have magnetic moment aligned with a field corresponding to the quantum number, which is equal to ms equals minus 1 by 2. The high energy state will have the spin magnetic moment opposite to the field, which corresponds to the quantum number ms equals plus 1 by 2. So this is exactly as shown. So this is a Zeeman splitting in the presence of magnetic field. The unpaired electron splits into ms equals plus 1 by 2 and ms equal to minus 1 by 2. And ms equals minus 1 by 2, which is aligned with the external magnetic field. And corresponding energy values are given by this expression and this expression. And ESR absorption spectra will be obtained exactly like this. And ESR derivative spectra will be obtained like this. Probably we'll be using later this picture. This is nothing but differentiation. So ESR derivative spectra. If an electromagnetic radiation of frequency nu satisfying this condition at nu equals the difference in the energy del E, which is nothing but E 1 by 2 minus E minus 1 by 2, which is equal to G mu B is present, then the transition between these energy levels occur, which is studied by ESR. So equation 4.8 gives the resonance condition for ESR observation. For a free electron, G equals 2.0023 in a field of 0.34 Tesla, then using equation 4.8, nu can be obtained as substituting all the values of G, mu B, and divided by H, we have 9528 megahertz. This frequency falls in the microwave region. Hence, microwave source and techniques have to be applied for the observation of ESR. Successful observation of the ESR spectrum requires suitable values for the frequency nu and the magnetic field B should satisfy equation 4.8 as it is given by this expression. For a magnetic field of 0.34 Tesla, nu frequency comes out to be about 9.5 gigahertz. Spectrometers operating around this frequency are often referred as X-band spectrometers. Spectrometers operating at higher magnetic fields, B equals 1.3 Tesla, with corresponding higher microwave, that is 35 gigahertz, are also available, and they are called as Q-band spectrometers. Now we will discuss elaborately about the difference between NMR and ESR. NMR is expanded as nuclear spin resonance and ESR is expanded as electron spin resonance. Here the energy difference between two energy levels del E is shorter than NMR, and we will have to apply only radio wave frequency. And definite nuclear spin value I is not equal to 0, and those molecules are NMR active substances. And here the energy difference between two energy levels del E is greater than NMR, and this will fall under microwave frequency. NMR active substances will absorb microwaves. Substances must have at least unpaired electrons. ESR active substances, and in NMR, different energy states are produced due to the alignment of the nuclear magnetic moments relative to applied magnetic field, and the transition between these energy states occur on the application of an appropriate frequency in the radio frequency region. NMR absorption positions are expressed in terms of chemical shifts. Nuclear spin-spin coupling causes the splitting of NMR signals. And in ESR, the different energy states are produced due to the alignment of the electronic magnetic moments relative to applied magnetic field, and the transition between these energy states occurs on the application of an appropriate frequency in the microwave region. ESR absorption positions are expressed in terms of G values, Lambda factor. Coupling of the electronic spin with the nuclear spins, what we call this as hyperfine coupling, causes the splitting of ESR signals. Conclusion. The interaction between the electron spin energy levels of a molecule and the microwave radiation causes transition between electron spin energy levels by the absorption of microwave radiation is called electron spin resonance spectra, ESR spectra. The conditions. Molecules having unpaired electrons gives ESR spectra. Examples: free radicals, transition metal ions, paramagnetic molecules like nitric oxide, oxygen, and so on. ESR spectra obtained in the microwave region between 2000 and 9600 megahertz. ESR is a sensitive and accurate technique that can be used to detect, characterize radicals, to study the dynamic of macromolecules, to probe defects in materials, to study reaction mechanisms and kinetics, to quantify radical and defect populations, to study electron transfer kinetics, to study electron spin dynamics. ESR is similar to nuclear magnetic resonance, but it detects signals from unpaired electrons instead of atomic nuclei. Now we shall discuss the total Hamiltonian direct dipole-dipole interaction and Fermi Contact Interaction. The electron in a system under investigation may or may not be completely free. If it is located in an atom or a molecule or crystalline environment, number of interactions exist in addition to one between electron spin and the external magnetic field. These will also contribute to the total Hamiltonian of the system. We shall now discuss about them one by one. The first one is electron kinetic energy. The kinetic energy term is due to the motion of the electrons, which is represented by minus h bar square divided by 2m del square. Internal potential energy. This is the potential energy of the electron under consideration in the field of other electrons and nuclei in the atoms, ion or molecule, which is usually denoted by B0. Crystal potential. If the atom or molecule or ion under consideration is located in a crystalline environment, the electrostatic potential due to all the charges surrounding the species of interest has to be considered. This potential, denoted by B crystal, will have considerable effect on the spectrum depending on its strength in comparison to the other contributions. The splitting of the energy levels due to this potential is called fine structure splitting. This contribution is almost zero in the case of free radicals in solution. However, it is quite appreciable in paramagnetic salts such as transition metal ions and rare earth elements. Electron Zeeman energy. This represents the direct interaction between the electron spin magnetic moment μs and the external magnetic field B, and it is given by HSB equals minus μs B, which is equal to minus G mu B S dot B. Nuclear Zeeman energy. This is the interaction of the magnetic moment μl of the nucleus with the external magnetic field for a single nucleus having spin I, nuclear spin, that is nuclear spin I, and it is given by HLB, which is equal to minus mu L dot B, which is equal to minus Gn mu n I dot B, where Gn is the nuclear G factor and mu n is the nuclear magneton. Nuclear electron spin coupling. Interaction of the unpaired electrons with the magnetic moments of the nuclei within its orbital gives rise to two additional terms, the nuclear spin coupling and the Fermi contact term. The splitting of the spectra observed due to this is called the hyperfine structure. The nuclear electron coupling is a direct dipole-dipole interaction between the electron and the nuclear magnetic moments, as this interaction depends upon the angle between the magnetic field and the line joining of the two dipoles. So this is a line joining. It is directional and is referred as the anisotropic interaction. Its magnitude is proportional to 1 by r cube, where r is the distance between the dipoles. For free radical in solution, since the orientation of the radical with respect to the magnetic field changes rapidly, this interaction averages to zero, and the hyperfine structure observed then is from the other mechanism, and this dipole-dipole interaction is given by this expression, equation 4.12. So the dipole-dipole interaction is Gn mu B mu n times Si divided by r cube minus 3 S dot r I dot r divided by r cube. The second electron nuclear interaction is the Fermi Contact Interaction, which has no classical analog. This represents the interaction between the nuclear moment and the magnetic field produced by the electron spin at the nucleus. This depends on the finite unpaired electron density at the nucleus, which is possible when it occupies an s orbital, as p, d and f orbitals have moved at the nucleus. the corresponding electron densities are 0. This interaction is independent of the orientation that is given by HF equals 8 pi by 3 G Gn mu b mu n psi squared S dot I, which is equal to A S dot I. The remaining factor we can consider as A, which is nothing but hyperfine splitting constant. And of course, where psi is the electron wave function at the center of the nucleus. Since the Fermi contact term involves only S electrons, the hyperfine splitting constant is isotropic. Other interactions. Some of the other interactions which are of interest in crystalline paramagnetic substances are electron spin orbital coupling, nuclear moment, electron orbital coupling, electron orbital magnetic field coupling, and nuclear electric quadrupole energy. The last one is of significance only for nuclei with I is greater than 1 by 2, as we will be concerned mainly with systems in which electron spin couples with the protons I equals 1 by 2. It is not of that much significance. Hence, the total Hamiltonian is the sum of all these contributions. However, less significant contributions can be left out depending on the systems of interest.